Hi everyone, welcome to the presentation of Deadlock Prediction Well-Generalized Dependency. My name is Jinpeng Zhou. I'm from University of Pittsburgh. In this work, we focus on dynamic detection of generalized deadlocks in multi-threaded applications. The generalized deadlocks consist of two types of deadlocks. The first type only involves locks and is called resource deadlocks. The second type involves at least one condition variable, and we call it communication deadlocks. Although there are many deadlock detectors, most of them can only handle resource deadlocks. To our best knowledge, there exist few detectors for generalized deadlocks. Checkmate is the previous state-of-the-art tool. It uses model tracking to explore all possible thread interleavings to expose the potential deadlock. It has a high runtime overhead and low scalability. In our work, we aim to provide effective and efficient detection for generalized deadlocks. We first define the concept of generalized dependency to represent the hold and wait relation involving locks and condition variables. Then we define several rules for the generalized dependency to make it more practical for real applications. In the end, we implemented a prototype named onHam based on the generalized dependency. The generalized dependency is defined as a triple, indicating thread T waits for resource R while holding all resources in a specific set. The resource can be locks and can also be signals on condition variables. Different dependencies with no conflict may build a chain, and a cyclic chain indicates a potential deadlock. Now, let's use an example to illustrate how generalized dependencies represent hold and wait relation, and how generalized dependencies help the deadlock detection. The example is from memcached, where a maintenance thread collaborates with multiple worker threads for each maintenance. For simplicity purpose, we only list one work thread here. Now, let's assume the first maintenance starts. The maintenance thread Tm proceeds to the second lock activation. It is waiting for the lock L2 while holding lock L1. This hold and wait relation can be represented by dependency D1. Then, when the thread Tm moves to the wait operation, it is waiting for the signal while holding the lock L1. Similarly, this relation can be represented by dependency D2. Note that the lock L2 from the second parameter of the wait operation is the associated lock to the condition variable. The thread Tm will implicitly release the associated lock before waiting, and will also implicitly acquire the associated lock after waking up. That is, when the thread Tm is waiting on the condition variable, the associated lock L2 may be available for other threads to acquire. So the worker thread Ti is able to acquire the lock L2 and send the signal. When the worker thread is releasing the signal, we know that the worker thread has been holding the signal since the first statement. That is, when the worker thread was at the first statement, it was waiting for L1. It was waiting for L2 while holding the signal. And this relation can be represented as dependency D3. Now, for simplicity, let's assume the first maintenance completes, and later we have the second maintenance starting, and the maintenance thread Tm wait on the condition variable again, and the worker thread Ti proceeds and acquires the lock L2 and sends the signal for the second maintenance. This signal forms a hold and wait with a lock from the previous maintenance. And this hold and wait can be represented as dependency D4. Now we have 4 dependencies, and we may notice that there's a cycle between L1 and the signal. And this cycle indicates the potential deadlock. As a matter of fact, when the deadlock happens, The thread TM is waiting for the signal from TI while holding the lock L1, and the worker thread TI cannot send the signal because it is stuck in the previous maintenance, waiting for the lock L1. At this moment, both threads cannot move forward. Now let's take a look at the practical rules defined for the generalized dependency. The first practical rule is called non-conflicting signals. It defines that common signals held in different dependencies should not cause any conflict. This is based on the fact that signals are not mutually exclusive. Let's take a look at the dependency D1 and D2. They hold a common lock LC. Since the lock is mutually exclusive, only one thread can hold LC at one time. Then the dependency D1 and D2 have a conflict. For dependency D3 and D4, they have a common signal, which is not mutually exclusive. Then the two threads can hold the signal concurrently, and these two dependencies have no conflict. The second rule is called conflicting signals. It defines that dependencies waiting for conflicting predicates have a conflict. This is based on the fact that two wait operations with conflicting predicates cannot happen concurrently. In this example, we have two wait operations associated with two conflicting predicates. The predicates full and the predicates empty cannot be true at the same time. Consequently, these two wait operations cannot be performed at the same time. Given these conflicting predicates, the dependency D1 and D2 have a conflict. In order to identify conflicting predicates, one solution may be tracking and analyzing memory accesses. However, we note that the conflicting predicates are typically protected by the same lock, which is the associated lock. Then, instead of analyzing the predicates, we can simply check the associated lock to infer conflicts. To be more specific, if two wait operations have the same associated lock, we will assume that these two wait operations have a conflict. The third rule is called spurious cycles. Spurious cycles should not be treated as real deadlocks. This is based on the assumption that real-world applications are well tested, so that obvious deadlocks should not exist. The example here shows a obvious deadlock. The thread T1 is waiting for signal from thread T2, and the thread T2 is waiting for signal from thread T1. Both threads will definitely deadlock upon the first statement. And if the real-world application has such a deadlock, then the deadlock will definitely happen and the bug will definitely be fixed before the deployment. Now, let's take a look at the prototype on hand. On hand is a dynamic library built for pthread-based applications. It records dependencies during execution and proves redundant dependencies for performance optimizations. It detects cycles of dependencies at the program exit and extends the reachability graph concept from our log. For more details, please refer to the paper. Here, let's directly take a look at how Anhan performs on real-world deadlock bugs. We collected 9 bugs from different applications, and based on our evaluation, the Anhan is able to detect all known deadlocks and uncover 2 new deadlocks. Meanwhile, Anhan reports 1 false positive due to memory reuse and 2 false positives due to ad hoc synchronizations. The memory reuse refers to a synchronization object reusing the memory address of a previously freed object. The consequence is that we may treat the consequence is that these 2 synchronization objects may be treated as the same object, result in unnecessary dependencies. As to the ad hoc synchronization, it may introduce implicit happen before relation, which cannot be recognized by Anhan. However, the memory reuse and ad hoc synchronization are the 2 common issues for most existing dynamic deadlock detectors. We also evaluate the detection time for unhand. Based on our observation, the unhand's detection time is significantly less than undead. This makes sense because undead is using the traditional DFS-based cycle detection, while unhand is built on the reachability graph. We also run unhand on benchmark applications, including parsec benchmarks and 6 real-world applications. The overall performance overhead is 2.7%, and there is a 2.2% overhead for the logging phase and 0.5% overhead for the detection phase. We notice that there's a 15% overhead for the application Fluid Animate. This is because the Fluid Animate has 92 synchronization objects and 1.7 billion synchronization events within 20 seconds. We also evaluate unhand's memory overhead by splitting the application into large footprint and small footprint based on their memory consumptions. For large footprint applications, unhand's memory overhead is around 2.7%, and for small footprint applications, the memory overhead is 89.5%. This is because unhand itself consumes some memory for its internal usage. The overall memory overhead is 8.2%, which is slightly higher than undead. This makes sense because unhand needs to record more information to detect a broader type of deadlocks, while undead is just a resource deadlock detector. We also built another version of unhand, which records all the dependencies it encounters during the execution without pruning redundant dependencies. And comparing this version with the original unhand, we can see that the pruning redundant dependencies reduced the overall memory overhead from 33.2% to 8.2%. In summary, we define to detect the generalized deadlocks. We define the concept of generalized dependency, which represents the hold and wait relations involving logs and condition variables. We also define practical rules for the generalized dependency. These rules are used to determine whether two dependencies have a conflict and to determine whether a cycle indicates a real deadlock. And our prototype unhand is able to detect all known and new deadlocks. It only introduces around 3% performance overhead and 8% memory overhead. It generates few false positives caused by memory reuse and ad hoc synchronization. And these are the two common issues for most existing dynamic deadlock detectors. And that's it. Thank you for watching.